We will now begin with our first session of the day, Ethics and Fairness in AI. Our speaker for the first session, Dr. Jon Kleinberg, is the Tisch University professor in the departments of Computer Science and Information Science at Cornell University. His research focuses on the interaction of algorithms and networks, the roles they play in large-scale social and information systems, and their broader societal implications. Dr. Kleinberg's address will be followed by a short Q&A session, so I request all participants to post questions in the Q&A tab during the session. Please do keep them brief. May I now request Dr. Kleinberg to deliver his address. Over to you, sir.
Thank you very much. I'm going to share some slides that I have, and you can let me know if that works. Okay. Are you able to hear that and see that?
Yes, clearly we can see the slides as well.
Great, thanks very much. And feel free to interrupt at any point if we can adjust anything. Well, so thanks very much for having me, inviting me to take part in this event, and as part of highlighting some of the priorities of this very impressive initiative, which involves both so much talent being brought together and also a focus on issues and themes that are extremely timely and extremely important. What I wanted to talk about during this period was some of the ethical and societal implications of AI, algorithms, and computation. And of course, this takes place at a time that's very challenging, that contains a lot of pain for a lot of people due to the pandemic, due to some of the inequities that has exposed. And I think a lot of us with technical backgrounds are thinking about how we might be able to use some of the tools at our disposal to help, and some of the ways in which the platforms that we're building play a role in all of these issues. This is certainly something I've been thinking a lot about over the past few years, and I wanted to tell you about some of the work that we've been doing. This will be include joint work with my PhD student, Manish Raghavan, and three faculty colleagues from three different areas: Jens Ludwig in public policy, Senthil Mullainathan in behavioral economics, and Cass Sunstein in law. So in order to talk about some of these ethical and fairness issues, I, in a sense, have to first start in the 1990s, when a theme that had been really prominent in the field of human-computer interaction began to make its way into all of computer science, really. And that was the idea that we weren't simply building technical systems, but rather that there was a second axis to what we were building, in a sense, a social axis. Because as we built technical systems, as we walked around in this one-dimensional space of the technical, we kept bumping into things that didn't make sense to us. We would discover that we were making social or economic decisions, and they would have implications beyond the intent of our original design. And so through the whole long arc of the web's growth in the 1990s, we began to develop this idea of socio-technical systems, things that lived in the space with these two rich dimensions, both the social and the technical, and the understanding that we really had to understand both of them. That if you designed only technical systems, you'd be perpetually surprised by the way in which they rebounded against your best efforts because of the social and economic forces at work. And conversely, if you were thinking about social and economic systems, you could often miss the extent to which algorithms, AI, and computing were playing a role in even what appeared to be offline systems. And so we worked on these systems, but we discovered something else was going on. As we built them, unexpected things continued to happen. We would discover, for example, misuses of information, violations of privacy, polarization and conflict happening, bad decisions aimed at individuals, discrimination against groups, all happening in these systems that we were building. It was as though even moving in this two-dimensional space, we were bumping into some sort of third dimension that we weren't able to see. And indeed, there was a third dimension, and it's been gaining prominence as a focus for technical research over the past 5 to 10 years. It's what I might call, floating above these socio-technical systems, a normative dimension. The question of what is the right way to build these systems? What is the ethical way to build these systems? What are we trying to achieve from them? What are our societal goals in creating these systems? And this, in a sense, was, I think, in a sense, a surprise to the field, although it shouldn't have been, that just because an entity creating a digital system or an online platform, just because they understand social or economic principles, doesn't mean they will necessarily use them for good. That is a separate question. And that is what informs a lot of this current research that is thinking about ethical, normative, and fairness dimensions of AI and computing. So this is what I wanted to talk about, how in this three-dimensional space, we're thinking about some of the societal implications of the technologies that we're building, both in the online world and the ways in which they interact with the offline world. So what's happening at this online-offline nexus? One way to think about it is to think about the ways in which we've taken some of the ideas of online socio-technical systems and begun to apply them in the offline world, right? So if I think about a recommendation system, for example, right? So this is a screen from a movie recommendation system from Netflix in particular. And it is powered, the way a lot of these online platforms are powered, by a huge amount of data about users. And we all have some sense of perhaps what a recommendation system is doing when it makes a prediction about whether we'll like a certain movie. It is looking at past data from us, right? So it's taking a complex thing, namely all of our collective tastes and preferences. It's boiling them down to a set of feature vectors. It's running them through a machine learning algorithm that then makes a prediction. It estimates a probability that we will like a particular movie. And in this context, people began asking themselves, if we can do this in the online world, if I can predict whether you'll like a movie, maybe I can look in the offline world for places where there are also prediction problems, right? And these kind of prediction problems are numerous. When you apply for a job, for example, you often submit a resume to a prospective employer and they evaluate the resume. And in that way, we're doing something that at a very high level is similar. We're taking your past educational and work history, which is a very complex thing, played out over many years. We're reducing it to a collection of features, your resume. It gets handed to a decision maker, a hiring committee, and they in turn attempt to predict something. Actually, what they're predicting, whether you'll be a good employee, whether you'll work well at their company, whether you'll work well with other colleagues, it's unclear exactly what they're predicting. And I'll come back to that because it's hard to figure out ever what's going into a human being's decision. But there's some sense that the pipeline here feels somehow similar to us. And so people began to ask, could we use algorithms in a domain like hiring? We could ask a similar question in education. So this is a portal to my own institution where you can apply to be an undergraduate at Cornell. A very similar thing is happening. We're taking your early education, reducing it to a set of features. It's passed through an admissions committee, which is again making some complex decision that's hard to quantify because it's being made by human beings. So in all of these contexts, we're doing something that we might call screening for hiring, for education, for things like credit, where we have to decide, make a prediction, will you repay a loan? Even in areas like criminal justice, where a judge may be called upon to decide if someone, if released from jail, will commit a crime in the near future. All of these have this pipeline that I'm showing here, where an individual gets mapped to features, passed through some decision-making object, and a prediction is made. And we think of these as so-called high-stakes decisions because the outcome matters a huge amount to the recipient of that decision. It matters a lot whether you get this job, whether you get admitted to school, whether you get this loan, whether you have to await trial in jail or in the community. This is not, of course, to say that what's going on in the online world is low stakes. It is low stakes whether the algorithm was correct that you would like a particular movie or whether you would be interested in a particular article in your social media feed. But we also know that you can take 100 billion of those very low stakes decisions and, for example, the choice of what news to show people, and it can add up to something very high stakes, such as the formation of public opinion in a country as an election looms. So all of these are important, but I would focus on these offline tasks as individually high stakes. Each of your decisions matters a lot to some individual. Each of your mistakes is costly. And as a result, we have to think here about the risk of bias. How does bias come into these high-stakes decisions, both for human decisions and for algorithmic decisions? And this has become a very active area in AI, machine learning, and computing over the past few years. Now, if I'm going to talk about bias by algorithms, then we should first say a few things about bias by human beings, because bias by human beings is one of the most recurring behavioral properties that we see in people, bias in their decision-making. It happens not just in humans with bad intentions, but even in humans with the best of intentions. And how does it work? Well, obviously, there's only a limited amount I can say here in the limited time that we have, but there's a long line of empirical research which really gathered momentum in the 1990s on implicit bias in the evaluations that humans make, such as they would make in screening decisions. I'll just walk you through one example, which is this plot here on the right-hand side, which shows reviews of grant proposals by researchers in Europe. And so what happened was a grant proposal would be submitted to a review committee, and they would assign the principal investigator a so-called competence score. How competent do you think this researcher is in carrying out the research? Now, two social scientists in the 1990s, Christine Vanavos and Agnes Vold, wrote this influential paper in Nature, in which they analyzed these competence scores, and they compared them to measures of the impact of the researcher being evaluated. And they tried every way they could to characterize these researchers by impact. They looked at the number of publications they had in high-impact venues, their lifetime number of citations, their success on achieving past funded grants, and so forth. And every way that they could do this, what they found was that male researchers of a given impact score on the x-axis here, right? So let's think about this particular level of impact. We're receiving on average significantly higher competence scores by this subjective evaluation than female researchers, right? That even if there was no, right, this is not a statement about whether there was intent to engage in this disparity, but whether or not there was intent, there was this gap that was extremely troubling, that was pernicious in the way that funding was being allocated. And this is, in fact, one of the more robust findings in the study of evaluation mechanisms, that you'll see these gaps even when you control as carefully as possible for similarity among the people being evaluated. Even when you create synthetic people who actually are identical in every way except their name, and you present these synthetic applications or resumes to evaluation committees, you'll find that one group fares worse than the other. So this is the challenge of implicit bias. It goes on whether we intend to or not, and it's an aggregate effect, right? It has the challenge that we can see that on average there's discrimination happening, even though we can't say which person in particular is engaging in the discrimination. We know that it's happening on average. Now, let's look now at the case of algorithms. Algorithms, in contrast to humans, have no direct incentive to exhibit bias. Unless someone programs them to tell them to engage in bias, they're not going to do that, because they don't even necessarily know what these groups are that they're looking at. Despite this, one of the findings of this area over the last 5 to 10 years is that there are many sources of potential bias in algorithms, even though the algorithms themselves don't have these incentives. Why is that? Well, the bias can come about in a number of ways. First of all, as I'm sure a number of you have seen in news coverage of this, if the data that you're working with contains earlier human bias, an algorithm trained on it might exhibit that bias. So for example, if I were to train an algorithm to make funding decisions on grant proposals, and I fed in the past scores that researchers had gotten on earlier of their applications, including this competence score, then the algorithm might learn to be biased by gender. Why? Because the data contains that bias. Similarly, my choice of objective function might have similar issues. If I were trying to train it to learn to predict competence scores so as to match what human experts had done, then it would in effect end up matching this gap, because that's what it's being trained to do. So in all of these cases, an algorithm may end up engaging in bias even if it has no initial incentive. And notice how important it is in this analysis to think about the relation between bias and some notion of interpretability of the system, right? Because we know how we built the algorithm, even though it's very complicated, we can say something about the ways in which it's engaging in bias in a way that with humans, it's actually quite difficult. We don't really know why people make the decisions that they make. Now, when we think about human bias and discrimination, there's one more thing that's useful to point out, which is this issue of intent. And so we often think, and this is true in the laws of many countries, I'll use the terms of art in US discrimination law, but this distinction shows up in the legal systems of most countries, that disparate treatment is the notion of intentional discrimination, that I'm deliberately favoring people on the basis of what we think of as protected attributes like race, gender, national origin, religion, age, or others. Whereas disparate impact is to say that regardless of intent, if a screening decision has a disproportionate adverse impact on some protected group, then potential discrimination in fact has happened. And now the burden shifts to the decision maker to establish the business necessity of this decision that they're making. Thus, for example, if we have a job that requires people to be extremely tall because that's physically necessary for reaching high objects, then an employer could argue that they're selecting for tall people, even if this has an effect, for example, if it creates a disparate impact by gender. If, on the other hand, people hiring software engineers were to include a requirement, say, based on height, that might be viewed as a disparate impact that had no business necessity. There's no obvious reason why height was going to be necessary for software engineering. So the problem is, of course, when disparate impact is happening and we want to figure out is it intentional or not, it can be very hard to tell if a human decision maker has engaged in this action deliberately. One reason is they might lie. When faced with this fact, they might give you a misleading reason why they made the decisions they made. But there's a deeper and, in a sense, more fundamental reason why it's so difficult with humans to tell why this is happening. And that is they themselves might genuinely not know their rationale. Even when you ask them to explain, they might be happy to give you a reason. And even, again, someone with the best of intentions, trying to help you diagnose the problem, interested in fixing the problem, might provide you with their rationale for why they're making decisions, and they might simply be wrong. This principle has a long history in behavioral science experiments, going back to influential work of Nisbet and Wilson in the 1970s, where what they would do is present subjects with a decision task with a known but hidden twist in the environment, right? They would put people in two different situations, change the environment subtly, observe that the decisions were different, and then ask people why they made the decision they made. People would report many different reasons, but almost never would they report the one thing that was actually different between the environments. They wouldn't pick up on it, and they would come up with reasons that weren't related to that. Here's an example of how one of these experiments worked. They would stand outside a store with a rack of articles of clothing, and they would ask people to pick their favorite one. Now, it was a known fact in psychology experiments at the time that you could induce people to favor things on one side of the arrangement over the other simply by positioning effects, right? In the same way that a stage magician might force a card on you, you could set up a rack of clothes so that people would overwhelmingly pick the thing on the right. However, when you would ask people, why did you choose this particular article of clothing, they would say it was because of the color, they would say it was because of the style. They would give lots of reasons, but people wouldn't say, it's because you arranged it to cause me to pick the one on the right. Even though we would rearrange things, they would rearrange things, and people would again pick a different thing that was also on the right. So, and they tried many experiments of this sort. You ask people to watch a movie, and in one condition, it's quiet. In the other condition, there's some annoying noise going on in the background. You ask people how much they like the movie. People give different answers, and yet no one mentions that that the only distinction was the noise in the background. So this notion of telling more than we can know, even when people give reasons, those reasons might not be correct. And I think this is actually interesting in turning the notion of interpretability for algorithms sort of on its head in a way, because we often talk about how algorithms are black boxes, they're inscrutable, and that's certainly true. Algorithms are very complex. But what we need to remember is that humans are very complex as well. And just because a human decision maker can present the illusion of an explanation doesn't mean it's the real explanation. So that's a key argument behind some of the work that we've been doing, that well-regulated algorithms can make discrimination easier to detect. Now, well-regulated here means if the algorithm is made available to people who are trying to audit discrimination. Clearly, an opaque secret algorithm doesn't make the situation any better, because if I have an actor with bad intent, and I give them a powerful tool like an algorithm that they keep secret, now I simply have an actor with bad intent and a powerful tool at their disposal. But if the algorithm is made transparent, then the point is that we can actually analyze the decisions made by the algorithm in ways that we can never have done with humans, right? So we can't necessarily read the code and understand the algorithm, right? We know that computational undecidability, we know the challenges in software engineering mean you can't necessarily read code and understand what's happening. But if the algorithm is built according to the standard machine learning pipeline, I can do many things that I can't do with a human. I can ask, what are the features that the algorithm is using? I could ask, what labels is it being trained on? What is the objective function being maximized? I could, in principle, build my own algorithm from the same data and see if it exhibits similar disparate impact. I could, for example, create synthetic instances and probe the algorithm with that. All of these are things that are very, very hard to do with human beings. I can't really ask a human hiring committee, what is the objective function that you maximized, right? All of you who have sat on hiring committees, in your mind, you'll typically have some qualitative notion of the criteria that you're looking for, but it has nowhere near the specificity, nor do you adhere to it with anything like the same fidelity that an algorithm will. That's not to say the algorithm necessarily has the right objective function or a good objective function or one that produces the outcome we want. It simply means that we're at least able to examine the objective function. We're able to experiment with it in a scientific sense and thereby audit some of the effects of discrimination in ways that we simply can't with human beings just by asking them questions. So once we have this notion of being able to analyze the algorithm, what are some of the things that we can learn from it? Well, so here's one of the ways in which we might be able to characterize disparities. And for the next few minutes in the talk, I want to get a bit into some mathematical models of what's going on that tries to instantiate some of these principles about analyzing a machine learning pipeline, considering issues of complexity and interpretability in a more concrete way. So in order to do this, I'm just going to introduce a very small amount of mathematical notation from the areas of AI and machine learning. So I think about individuals, and I'm evaluating them, say, for hiring. Each individual has a feature vector, let's call it X, which has some number of dimensions. And in my hiring application, I have an objective function. Let's say as a function of these features, f of X is the future productivity of the person who's applying, right? And that's what I'd like to maximize. I'd like to hire productive workers. Now, I'm concerned about discrimination. And so I imagine that there are two groups. There's an advantage group, which has, over time, in aggregate, received socioeconomic advantages from society, and a disadvantage group, D, which has received fewer socioeconomic advantages from their path through society. Now, in what sense is group D disadvantaged relative to group A? Well, if I know the features of someone, I actually don't care what group they're in. The notion of disadvantage is actually simply in the frequency of features. So in particular, features that lead to higher productivity are more abundant in group A than they are in group D. Again, so if we fix the features, it didn't matter which group you're from, but it's much harder to obtain advantageous features when you're in group D. So this means we can characterize what I might call structural disadvantage, which is the average difference in productivity between group A and group D. Right? So in group A, I sum over all possible feature vectors X, the frequency of that feature vector times its productivity, and I take the difference with that same computation in group D. Again, f of X doesn't care what group you're in, but the allocation of features is differently distributed. Now, I could do that for any function. not just this productivity function, but for any function v, I could look at the disparity between the average value of v in group A and the average value of v in group X, in group D. And with that in mind, I could then ask something about where bias is coming into the system from this machine learning pipeline. Let's remember that there's already disparate impact in society, right? D of F, this structural disadvantage, which is typically not zero, already means there's already disadvantage before the algorithm ever arrived on the scene. But the algorithm might cause new sources of disparity. What are some of these sources of disparity? Let's walk through these one at a time. First, the algorithm designer typically doesn't know the true function, so they invent a function of their own. Let's call it g instead of f. Second, it's very hard to use every possible feature about an individual, so they'll typically use a reduced representation, r of x instead of x. Now, this reduced representation is a very short vector instead of a long vector, so we can't use g, which is designed to work on this long vector x. We have to use some other function, let's call it h, that works on this short vector r. So instead of g of x, I'm really computing h composed with r of x, right? So I apply r to x to get the reduced feature vector, and I apply h. But finally, I can't really even use h because I have to train this on some finite amount of training data. I don't know any of these real functions. So my training procedure on a small amount of training data produces not h composed with r, but t composed with r, this trained function. And in the end, I deploy this machine learning algorithm into the world. And what I end up with is a disparity, but it's not d of f, it's d of t composed with r, right? My reduced representation, my trained function on my training data. Now, what's interesting is that I can actually decompose d of t composed with r, the disparity that I see in practice from the machine learning algorithm, by writing it in the following extremely expansive way. It's the structural disadvantage plus this term, which cancels d of f, plus this term, which cancels d of g, plus this term, which cancels d of h composed with r. Right? If you work this out, this is just a very elaborate way to write d of t composed with r as a kind of telescoping sum, if you will. But it now has four terms, each of which has meaning in the policy discussions around machine learning. The first is the structural disadvantage, the disparities that existed before machine learning ever arrived on the scene. The second is the bias from the choice of objective function, or label. Right? It's the difference between the disparity from g with f. The third is the disparity that comes from using h instead of g, and using the reduced representation, the bias from my choice of features instead of using a fully rich feature representation. And finally, d of t composed with r minus d of h composed with r, the bias from the training procedure. And so, in a way, simply by writing down this very simple model, we see that we actually can characterize the disparities into the different ways in which our choices in the machine learning pipeline, plus the upstream structure that society already had, can create these forms of bias. Let me dig slightly further into this model, and in particular, think about one particular aspect of this, which is the idea of reduced representations, the idea that we essentially never have the full set of features that we need. Okay, and to think about how this leads to an opportunity to investigate some of the bias through these notions of interpretability and analyzing the pipeline. So let's think again about this model. So applicants are described by feature vectors. And again, I'm just reviewing the model. For the examples I'll use, we'll think of these feature vectors as Boolean, just 0 or 1. We have a productivity function. And again, my plan is to sort by the values of the productivity function. So I'm hiring people. I sort, and then I admit the top R fraction of applicants for some fraction R. And again, there's an advantage and a disadvantage group. And the function f, once again, does not care what group you belong to. The disadvantage is happening for this other reason, that advantageous features are distributed in greater proportion toward group A than to group D, and disadvantageous features more toward group D. Right? So if X is a better feature than X prime because it produces higher productivity, then it's more overrepresented proportionally in group A. Let me walk through an example of how this might happen on an extremely concrete classification problem. I've made it simple enough that we can sort of work through it just on the slide. So this is obviously simpler than any function we would ever see in a machine learning application, but it's one that our human brains in real time can kind of understand. Let's imagine I'm hiring, and in my toy example, there are only two features, x1 and x2. And the true criterion is the conjunction of x1 and x2. Maybe x1 is how you did, I'm hiring, how you did in school, and x2 is how successful you are in a work environment. Okay. Now, the advantageous, or how much you can demonstrate success in a past work environment, let's say. Applicants from Group A have each of these features set to 1 independently with probability 2/3. Applicants from Group D have each of these features set independently to 1 with probability 1/3. So I get this little truth table, right? So this row says applicants from Group D with each of these set to 1. They would have an F value of 1 because, again, F is simply whether these are both set to 1. What fraction are they in the population? Well, half the population, let's say, is from Group D. There's a 1/3 chance they have someone from Group D has this set to 1, a 1/3 chance they have this value set to 1. So a half times a third times a third is 1/18. And in this way, I can fill in the entire truth table with these values. And notice, for example, that among people who have F set to 1, 4/18 of the population is people from Group A with this property, and only 1/18 is from Group D. Right? Once I know x1, x2, I don't care about group membership. I know this person is going to be a productive worker. But the distribution of these features is different. So if I were to hire people or admit people at a rate R up to 5/18, all the admitted people would have F value of 1, and only 1/5 of them would come from Group D. Right? That's the way in which I have structural disadvantage. Right? It would be hard to say that this decision maker is adding new bias to the system, but they're certainly reflecting the bias that was already in society, the structural disadvantage. Now, suppose we use a reduced feature representation, right? Maybe it's hard to collect both features. And so I only collect x1. Maybe that's because collecting x2 is simply too expensive. So for example, if x1 was education and x2 was work experience, maybe for most of these applicants, we don't actually have much information about their past work experience. Maybe I'm reducing the feature set because actually my decision will get too complicated. Not here in my example, but if you imagine we have 100 features and we'd like to reduce it to 20. We might do it for reasons of out-of-sample generalization. There are many, many reasons why we might do this. In that way, we would end up with a simpler truth table, right? So we've collected only this variable x1. And now what happens is that the average value of f of people with x1, we can work this out, is not 1 because it's averaging over all the possible values that x2 could take. The actual average value turns out to be 5/9, and half the population has this. So now at small admission rates, the average F value I get is 5/9, not 1. And the fraction that comes from Group D is 1/3, not 1/5. So I've gained in equity, more people are from Group D, but I've lost in efficiency. So simplification is often viewed in terms of this trade-off. A gain in equity, more people from Group D, but a loss in efficiency. But it also comes with some dangers. And I wanted to point out 2 of these dangers. One is this notion that simplification can transform disadvantage into bias. What do I mean by this? Again, so I have this simplified truth table, this approximation to my function on the right. In the original truth table, the one that had all 8 lines where I knew all the feature values, if you had asked me, would you like to know the group membership of this applicant? The answer is no. I actually don't care about the group membership of this applicant. I have everything I need to know. Once I simplify and only have variable x1, if you were to ask me that same question, would you like to know the value of the group membership? The answer is yes. In fact, I would like to know the value of the group membership if I'm trying to maximize F, because it helps me recover a little bit of the missing information about the probability that x2 is equal to 1. And in particular, if I were to learn group membership, I would end up with this truth table, in which someone with x1 equals 1 and group membership A actually has a higher value of F. So in effect, by simplifying, I've created this incentive to seek out the value of group membership. And it's a pernicious incentive, because if I were simply trying to maximize F and didn't care about equity, I would be using group membership in a way that favors A. Okay, so that's the sense in which simplification has transformed structural disadvantage, where the decision maker wasn't biased, they were just reflecting society's disadvantage, into overt bias, the incentive to seek out group membership and use it against the disadvantaged group. Now, what's interesting is how much this resembles and how much this really in a very simple way models what we think of as a basic mechanism for stereotype formation in real life. We know that in situations of, as humans, situations of low information, or snap decision making, we're more inclined to fall back on stereotypes and biases. And the interesting thing here is that what we can see in this model is that an 8-line truth table will do exactly the same thing if you hide information from it and instruct it to only care about this function f. Right? The very same thing where, lacking information, it will seek out group membership in ways that are pernicious. There's a second problem with these simplifications, and that is that it's never, in fact, the optimal thing to do in any case. Let's again go back to our truth table. And let's imagine we added one extra row in which, for members of group D, we collected the value of x2 and used it when it was equal to 1. Okay? So you could read this truth table from top to bottom. If both values are 1 and the person is from group D, we know the value is f, and let's admit them first. Then let's fall back to all the other choices. This truth table is actually better in efficiency. We're admitting people for every admission rate with higher average values of f. And it's better in equity because we're admitting this collection from group D first. This too resembles something that we see in practice, right? If I were a company, I said it's costly to collect work experience, but I'll create an internship program for members of group D and observe them working, and I'll take the ones who do particularly well. What I've done is simultaneously increased my efficiency. I'm getting a better average value of f, and I'm increasing my equity with more people from group D. So that, in a way, is a sort of way to think about the process of simplifying a complex decision rule and two of the dangers that it introduces. One, right, that once we've simplified, we're at the sort of unstable point on the landscape, where in one direction, we fall into incentivized bias, where we have an incentive to seek out group membership, and it's a pernicious incentive because it works against group D. In the other direction, we have what you might call Pareto-Improvement, where by modifying this decision rule, we can simultaneously improve efficiency and equity. And a basic result that Senthil Mullainathan and I proved last year is that this is actually true for every Boolean function f, for every Boolean function f with real valued outputs. And for every simplification of it, we have both of these phenomena happening. There's always an approximation that strictly improves in both efficiency and equity. So the simplification is never the best trade-off. And second, if my original approximation does not use group membership, then adding group membership as a variable increases efficiency and reduces equity. Right? So it creates an incentive to seek out group membership because it increases efficiency, and it's a pernicious incentive because it reduces the membership from group D. So this is a brief exploration into some of the ways in which building models of this can expose some of the issues inherent in these discrimination issues as they're reflected in machine learning algorithms, and also reflect back on our own practices as human beings, because we can see mirrors of ourselves in some of these mathematical models. There are many, many further directions here, right? This act of simplifying complex rules is something that's going to be ongoing, because in the end, the algorithms that we're building are becoming increasingly complicated. We're going to have to think about the ways in which we have to find reduced representations, find simplifications that are going to be comprehensible to their human designers, but also not perpetuate biases. And more broadly, I would again come back to this point that algorithms are in a sense allowing us a new level of concrete, explicit discussion about the decisions that we're making and the biases that enter into the process. And I think what's exciting about this area and what's exciting about the initiative represented by the Symposium is how many fields are going to need to play a role in setting these priorities, not just technical fields, not just computer science and applied mathematics, but areas like the social sciences, law and policy, business, and the humanities are all going to have to think about this new world that we're creating and some of the ethical and normative implications that arise as we do this going forward. Thanks very much.
Thank you, sir. I think there is no bias when we say that this was largely a very nuanced and erudite talk. So in the interest of time, we will just take maybe a couple of questions. So I'll dive into the first one right away. So the first question is, so the companies who are spending the most on AI development today are companies that have a lot of money to spend. A major ethical concern in AI is that will AI only serve to centralize wealth further?
Right. This is a great question, and I think this is a topic that a lot of research is being directed at, but I think much more needs to be focused on this particular aspect, because it isn't just about existing structural disadvantage. It isn't just about either explicit or implicit bias in decisions, but it's really also about the concentration of power that we're seeing. And I think this notion of about the amount of wealth that tech companies are amassing, the amount of power they're amassing, a lot of it is about concentration of power. And in a sense, you can think about these large platforms as, in caricature, as having created things that are the size, complexity, and power of nation states, in effect. But they've done it really without a constitution, without an executive branch or a legislative or a judicial branch. And you can see some of the internal processes that they're creating as beginning to try to simulate the functions of those things. But in a sense, they're playing catch up. They've reached a size and a level of power that we would be in much safer shape if these structures had been in place much earlier. And so I think we are trying to catch up to some of these issues, and they're very, very, very important to keep squarely in focus.
So we have time for one last question. So this one's, how does one overcome ethical challenges in AI, bearing in mind the cultural diversity and sensitivities across the globe?
I think that this is another extremely important question, that as we think about these issues, it's very important really to have a research community that is international in scope, that really reflects the legal systems of different countries, the norms of different societies and cultures, because I think there are many principles where we see alignment across these dimensions, but there are other where the diversity is important and the diversity is crucial. And I think elevating all the perspectives here and emphasizing that diversity is a particularly crucial feature for this topic as we go forward.
Thank you, sir. This brings us to a close of session 1. I thank Dr. Kleinberg for consenting to be here and conducting such a pertinent session. Thank you so much, sir.
Thanks very much. I really appreciate being here today.